methods are there in this class? 4, right? So there are 4 methods and 2 fields in this class, x and y. Let us for the time being make some assumptions which are very valid assumptions for how Java objects are laid out. Let us assume that integers are 4 bytes in Java, okay, which is true. Or if your machine is a 64-bit, has a 64-bit addressable memory, then it's actually 4 bytes for integers. And a class may also have a pointer like this, right? Let's say some other class B, F, G, or F, let's say multiple fields F1, F2, and C, some other class G1, G2, and so on, right? So I can have fields of other classes as well, right? So when we said we have these fields inside the class, we need to store these fields inside an object of each class. Each instantiation of class A should have space to store fields of 2 integer types. And what if it has more fields of some other class type? They also need to be stored there, right? So now there are 2 things here. One is a pointer and one is a real object, right? We had said that you allocate objects using the new keyword in Java, right? So now in order to understand where are these objects stored and so on, let's just recollect memory organization. As you might have studied at runtime there are multiple kinds of memory that are maintained by a particular runtime, right? What are they? Do you remember? There used to be some 4 or 5 classifications here. There is, yeah, right. So there is the stack, there is the heap, and then, yeah, there is some static region for global variables, and then there is some code region for code, storing code as well, right? And maybe there are some more regions as per need, but these are pretty standard. So let's first understand where are different things stored in a program. So if I have a method m1 like this, it has a parameter z, a return value, and it has a local variable t1 over here, right? So where are these local things stored? Parameters, local variables, any temporaries that you create, and so on. Where are all these stored in the runtime memory structure? On the stack, right? And why so? Because this stack is actually like a stack. So here you will have a stack growing for each method, isn't it? Any method that's called will have an activation record or a frame created on this stack. If foo calls bar, bar calls foo bar, you'll keep on adding frames to the stack. And when some method pops out, it has to go back to the previous method, and hence stack works very nicely. Last in, first out. When you pop out a frame, you come back to the previous caller's frame, right? I hope all of you are aware of this. So all the locals remain on the stack. And again, my question, why so? Why am I putting local variables on stack instead of, let's say, on the heap? So what happens to the local variables like this here? T1 is a local variable here and Z is a parameter over here. What happens to them? Is there memory available after the method M1 is popped off from the stack? No. So you want to make sure that a variable that's created locally inside a method is isolated from any other variable of the same name created outside the method or in some other method. You want to create a namespace for these local variables, right? That's why you put them on the stack. So that the stack frame, they are isolated from other variables of the same name on other stack frames or on the heap or a variable, static variable of the same name and so on, right? So they are isolated from them, and as soon as the stack frame gets popped off, these variables will get freed away, right? So anything on the stack goes away as soon as the frame of a method that allocated that memory is popped off from the stack. As soon as M1's execution is over, the memory occupied by T1 is freed up, for example here, and the memory occupied by the parameter Z is freed up over there, and so on. So what goes on stack then? Things that should be freed up once the method's execution is over, they should go on the stack, right? What about the heap? Second part, what should you allocate on the heap? We said objects go on the heap, but why? I mean, in general, what's the logic? We said you should allocate those things on the stack whose lifetime is bound to the method in which they are allocated. What about things on the heap? What should you allocate on the heap? Anything that requires dynamic memory, that's a textbook answer in some sense, right? There is one more thing here that I would like you to think about. Well, not a textbook answer. I mean, what I would say is, oh, it's very standard to say dynamic memory goes on the heap, but why? That's my question. Let's just add why to it. Yes. Well, I could have held the pointer to an object and kept the object on the stack as well, right? So all of you are right. Dynamic memory is important because, well, can you elaborate a bit? What do we mean by dynamic memory? Yeah, and why couldn't I have I allocated it statically itself? Yes, so if we don't know what would be the size of that memory, let's say I am allocating an array and I am allowed to resize the array at runtime, then I cannot keep on the stack because typically the size of the stack frame is fixed at compile time, right? So that's the reason. So you're right, that's one part of the reason. But let's say I know the size of an object, still I allocate it on the heap, right, most of the times. So why? Let's think about it from the perspective of the lifetime of things. We said if something's lifetime is bound to the method in which it's allocated, it should be on the stack. Right. So if you have an object that should be reusable across different methods, then can you allocate it on the stack? No. So if something's lifetime may outlive the life of the allocating method, then it has to be on some region which is still accessible after the method stack frame is popped off from the stack, right? And that's why you allocate it on the heap. So there are two things here. One is, well, it's a dynamically allocated memory, its size is not known, but even if the size is known, you cannot keep something on the stack if its lifetime may outlive, or if it may outlive the stack frame in which it is allocated. Okay. Yes. Good question. So what is static for? Let's move to the third one. What is static for? Globals and constants. So if it is a global variable, anybody can access it, let us say, right? So if it's a really global variable, if it's an object that you want to be accessed by everybody, then you will allocate it on the static region of the memory, let us say. But if it is accessible, let's say I am in a method bar called by foo. Bar allocates an object x is equal to new v and then returns it, return x, right? This object can be collected in foo, which called bar, and x is there. Let's write it a bit. So let's say my code is like this. I have foo and I collect the return value of bar somewhere, and in bar what I do is, well, there are return types here, some return type here, forget about it. What I do is x is equal to new, let's say some b, and then I'd say return x. Right? So this is a typical case where I cannot allocate this object on the stack frame of bar. Why can't it allocate it on the stack frame of bar? Because if I put it on the stack, as we said, it's local memory. As soon as bar goes away, the memory is gone. Right? So how would the stack grow here? You would say that, okay, foo calls bar, so you would have a frame for bar on top of the frame for foo, for example, if the stack grows upward. And once this is gone, once you come back to foo, this memory is not accessible anymore. So if you had allocated this object on the stack frame of bar, it will go away, right? So I would like you to think about it for a moment and try to understand why do we allocate memory in each region over here, right? So it's not necessary that everything should be allocated on stack or heap as per, let's say, language semantics, that, oh, everything that is allocated with new should go on heap. Not necessary, right? Things that outlive a method should go on the heap. Things that whose lifetime is local to a method can remain on the stack. That's first part here. And now let's come to static, as one of you asked. So if this object is this object supposed to be a global object? No. Who all should be able to access this object? Which methods? Bar and foo, right? I don't want some other method foo bar to be able to access it unless I have passed a reference to this object to that particular method, right? So it's not really something that's really global in some sense, and hence I don't need to allocate it on the static region, for example. On the static region, you would allocate things like, oh, there is some information about each class. What is the size of each class, for example? So anything that's should be accessible to everybody in general. It can go to another global memory, whether you call it static or declare it separately and so on. But on the heap, you still have a bit of controlled access. Only people who have pointers to the object can access it from the heap. Right? So that's one thing here. And then there is code region where you store the code of all the methods. So you need to load the code of all the methods that need to execute somewhere. That code's on the code region, let us say. This classification, the static and code regions may vary a bit based on the different implementations and different runtimes, but these two I want you to concentrate on more. This is memory that's local to a method, and this is memory that's shared across methods. But if there are pointers to that memory. Right? And typically the size of the stack is determined at compile time, it's fixed, and the size of the heap usually, the size of each stack frame is fixed. The size of the stack may grow as you keep calling methods, and the size of the heap is not usually fixed. There is some max memory, but there is no structure to it. Stack has a very well-defined structure. Oh, things go from one frame to another, either this direction or that direction, but heap is like an amoeba. Any direction, you can allocate objects anywhere in the amoeba. Okay. Any questions about what we taught just now, or what we discussed just now? So once you understand that, let's come back to this example. So we said, oh, memory for T1, since it's a local variable, we'll keep it on the stack. But what about these guys, X, Y, F1, F2, G1, G2? Where are they stored? Are they just plain variables? No, they are fields of some object, right? So whenever you create an object of class A, you need memory for an integer variable X inside it, you need memory for an integer variable Y inside it, and you need memory for variables F1, F2, G1, G2, but where will the objects pointed to by F1, F2, G1, G2 be? They will be in some other, they will be separate objects somewhere else, right? So let's try to understand how are these structured pretty much in detail. Let's remove this from now. This is our simple example, and let's assume that as I was trying to formulate, let's assume integers require 4 bytes of memory on our machine, which is typically true, and let's say references, if I have a reference variable bf1 like we wrote before, that also requires 4 bytes. Okay, and maybe characters require, how many you want for a character? 1 byte. Booleans maybe 2 bytes, whatever, right? So you can decide something. We'll check, in fact, on my machine what is it for each of the types of variables. We'll check it later on, but let's assume 4 bytes for integers and 4 bytes for references, because that's what we have in this example, right? So now can you tell me what would the structure of an A-type object look like? Oh, don't write with black. Difficult to erase. If I write with black, point out. Okay. So objects are on the heap because they are typically accessible by multiple methods. So in Java, by default, all objects go on the heap. And if you know C++, there is no object allocation if you write like this. If I write like this A, G, this does not allocate any objects. In C++, this means allocate an object on the stack. In Java, this is just saying that reserve memory for G wherever I am right now. If it is inside a method, reserve inside the method stack frame, for example. Only when you do something like this, G is equal to new A, is when you actually allocate memory on the heap. Okay, so memory allocation for objects is always on the heap by default in Java, though we would optimize this in the afternoon. And this memory is allocated only on processing this new instruction. When you just declare a variable, you are not allocating any memory for the object over here. Okay, so let's say we want to figure out the structure of a class A object. How many fields are required inside this object? 2. So what should be the size of each fields there? 8 bytes. So 4 plus 4, 8 bytes. And then I have 4 methods inside A as well, right? So given an object of a class A, object of class A here, I should be able to call methods of that type as well, right? How do I call methods of a class? If I declare like this, G is equal to new A, and if I want to call the method M3, what do? G dot M3. In M3, how do I access the fields of G? Or okay, let's take one example where we have a field. In M1, I have Z, which is the local variable. Where are X and Y coming from? They are the fields of which object? Fields belong to certain objects. So which objects fields are they? G. But how do I access it here? Either I just write X and Y, or I write this dot X and this dot Y. So when you just write X and Y here, which objects fields X and Y are you trying to access here? The object pointed to by this, right? And what is that object? That's the object on which you call the method. This is called the receiver object. Okay. So the receiver object here is the one pointed to by G. This gets mapped to the this pointer once you are inside the method. And when you say X, Y, this is essentially this dot X and this dot Y, which goes back to the object that you had created here. So this new A object will have some X and Y, and those X and Y are the ones that we are trying to refer to over there. Is it clear? So, okay, we are getting one more board. So, and probably after some time we'll get rid of both the boards. So anyway, so here I also need to be able to call methods using reference variables or this pointer over here, isn't it? So now you want to do something? Yeah. Thank you.
So can I ask you to put the other one this time?
Yeah, sure. Yeah, I think this doesn't have scratches, so this will be easier to rub. Ah, okay. I see. Okay. Actually, is it possible to keep this here and move that one here? Because we are. We have been writing there, and this board would be easier to clean, so we'll just keep it there. Anything which we need for future reference, we'll write here. That one we'll use as our running board. Okay. Yeah, better. Okay, so let's draw the structure of a class A object over here for the example that we have. So we need space for two integer fields inside a class A object, and then we want to be able to call one of the four methods M1, M2, M3, M4 as well, right? So there is a special data structure. See, does the code of the methods M1, M2, M3, M4 change for different objects? No, right? So the code is common. Since the code is common, do I need to copy paste the code of all the methods inside all the objects? No. So I can store it separately for each class, right? The values of fields may differ. If I create an object of class A at one place, I may put 10 and 20 in X and Y fields of that object. If I create another object, I may put different field values inside it, but the code of the methods doesn't change, which means I can reuse the memory for the code of all the methods across all the objects of a class, and I can essentially maintain that separately. So let us say I maintain another table here which has addresses of all the methods, the place where it has addresses of the locations where the code of each method is stored. Okay, so let's say I have the address of, let me write it like this, a underscore m1, address of a underscore m2, class a, method m2, a underscore m3, and address of a underscore m4. So let's say the code for m1, m2, m3, m4 is stored somewhere in the code region of the memory, let's say. So this is the code of each of those methods, and this address points to the code of each method here. That's it. Okay, so this is what I have here, and now inside a class A object I need access to this table so that I can access any of its methods, and I also need to reserve space for the fields. So let us say at the first location, the 0th index of this object, I have the address of this table. Okay, and then I have space for, at index 4 I store the value of the field x, and at index 8 I store the value of field y. So what's the size of this object now? What's the size of an object of class A? Excuse me, 12 bytes. Sorry. This is 12 bytes, right? Assuming 4 bytes are required for integer and 4 bytes are required for storing addresses on my machine, right? And this table, which contains the addresses of all the methods of a class, is called the V table, virtual table. All methods in Java are by default virtual, right? So it's the table that contains the addresses of all the virtual methods, and hence it's called virtual table. One of you asked me about V tables yesterday. So what we have stored over here we have just stored the address of the V table of which class? Let's say V table underscore A, right? So each class has a V table which contains the addresses of the code regions where the code of each method is allocated, and a pointer to that table is what I store at in the beginning of each object structure, and then I store the values of its fields. Okay, so you can say that for class A I have this amount of memory extra consumed, this much amount of memory for the code of all the methods, and this amount of memory for storing the addresses of those methods in the V table, and this V table is shared by all the objects. Now if I create another object here, so let's say I did something like this, G is equal to new A, and let's assume there was a constructor, so I initialize these fields 4, 8, or let me not reuse 4, 8, let's say 1, 2. So here I'll store 1, here I'll store 2. If I say somewhere down the line H is equal to new A, and let's say this time I say 2, 3, then I would have another object created for A. Again it would have 12 bytes of space. The address of V table of class A would be the first thing at index 0, and then at index 8 I will store 2, and at in index 4 I will store 2, and at index 8 I will store 3, which is the value of y. And where are these objects allocated now? By default on the heap, right? So these all go in our big amoeba, which was the heap, and then a pointer to those objects is stored in the stack. So if I have if let's say this code appeared inside a method foo, what's essentially happening is these objects are allocated on the heap, and then a pointer to these objects is stored in the local variables on the stack. Let us say this was a local variable A, this was a local variable H. So on the stack frame of foo, let's say this is the stack frame of foo, I'll have a variable stored called G, which will point to this object here, and I'll have a variable called H, which will point to this object over here. Does that make sense? Any confusions here? So you allocate, whenever you see a new statement in Java, you allocate memory for the object on the heap. How much memory? Determined by the size of the object, as determined by the class structure to which the object belongs, the number of fields, which kind of field it is, let's say 4 bytes for each integer over here, another address for the V table, and all of that is clubbed together. Actually, in reality, as we will see now, it's not just 12 bytes, it's slightly more, because apart from the V table, we also store some more pieces of information here for the garbage collector to work, for locking to work at the runtime, and so on. So apart from the V table address, we'll have some more things. So in reality, how much memory is required for storing a class A object, we'll see very soon, but this is conceptually, let's say, what we want. The other things are language specific. If your language doesn't have garbage collection, it may not store some more information. If your language doesn't have locking, we don't need those bits for locking, for example, but we definitely need memory for holding the fields. We definitely need memory for holding a pointer to the V table. Make sense? Okay. Now let's look at another class here which extends this one. So let's say I also have b.java which extends A. So when it extends A, we had seen in yesterday's example that the parent fields don't go away. They also have to be given a space inside a class A, inside a class B object here. So there are two fields from class A, X and Y, both of them were integers, and there are two fields in class B as well, both of them are integers. So what would be the size of a class B object then, as per our schema on that board? 16 for the fields, and yeah, you need again a pointer to the V table, right? There are methods in class B as well. So now let's draw the structure of a class B object. Let me get rid of this. I hope you are noting these things down, because we don't have slides for some of the topics today. Okay. If you didn't, then at least note down the structure of a class B object as we draw it now. So what should a class B object look like? First, it will have address of the V table of a class B type object, which is stored at the index 0. At index 4, which field would you like to store first over here? You can decide. You can either store the parents' fields first or the child's fields first, but let's come up with some algorithm. Let's say for now we'll store parents' field first. Okay, so let's say we store A's, what was the first field of class A? X. So let me call it A underscore X, just to distinguish same name fields between the parent and the child. So first I store A underscore X over here. Then at index 8, because that was an integer field, so 4 bytes are required. At index 8, I can store A underscore Y. Then at index 12, let me start with the child fields now. What's the first field of the child? X again. So let's call it B underscore X. And then I need one more. At index 16, let's say I store B underscore Z. And what would be the size of such an object? 20 bytes. 16 for fields and 4 for the V table. And now let's draw the V table. What should the V table of a class B object look like? So we need to keep all of them that we will be able to call, right? So if you go back, let's first copy A's methods over here. So you need space for calling A's methods. So let's say at index 0, I store the address of A underscore M1. At index 4, let's say I store the address of A underscore M2. Then at index 8, I store the address of A's M3. At index 12, I store the address of A's M4. So these are done. These were all from the parent. And now I again have M1 here. Is this M1 overriding the parent M1? Yes. And hadn't we seen yesterday that once in Java, at least once you have a child object, there is no way to call the parent method. Right? If there is no way to call the parent method, do I need to store it over here? Anyway, A underscore M1 there is no way to call it, like monkey's object was not able to call animal's tail at all, right? So we could just replace this. Let me cross it. Once I start processing my own methods, let me cross out overridden methods, because I have overridden them. There is no way to call them. So let's say this is actually address of B underscore M1 instead of A underscore M1. No, this is all I mean, this structure is determined statically, and of course this will be allocated at runtime, but it's the compiler that determines this structure by looking at the code of all the classes statically itself. So the size of an object is fixed by the compiler in the beginning. Okay, we'll see in fact that happening. Really depends. I mean, you could have looked at it and said, oh, I am overriding, so don't even copy it over there. Right? It's up to you. I mean, it's intelligent tweak if you want, right? But in reality, we don't need to store the address of A's M1 because we have overridden it. And now, do we have another method? Is it overriding any method in the parent? No. So let me store it separately. At index 16, let's say I store b underscore set. Right? So it appears as if I have really crossed off the address of a underscore m1 there, but of course it's an implementation thing, whether you want to write it and then cross it off, or you want to don't write it in the beginning itself, remember that your method is overriding it somehow, figure it out and so on. That doesn't matter, that's an implementation issue, right? Or rather that's an implementation trick. So what's the size of this v table now? 20 bytes. And there is a pointer to this v table stored over here. Apart from that, I have 16 bytes for the fields of a class B object over here. So this is how it will look. Is that clear? So if you are working with a language where you even override the fields of the parent, then you could have avoided storing a underscore x over here and directly used it for b underscore x. But in Java, at least fields are not overridden, fields are shadowed. They can still be accessed by typecasting a monkey object to an animal like we did yesterday. Or in this case, if you typecast this b object to an a type, you can still access this field. So you need to store memory for it so that its value can be stored separately from b underscore x. But there is no way you can call this method m1, and hence you can do this small trick to override a underscore m1 with the address of b underscore m1 over here. Is that clear? So when we say fields are bound statically, it has an interesting implication on the code generated by a compiler. Okay, so in this case, let's see, let's go to the simpler one first. Let's look at method m1. Okay, in method m1, I have said int t1 equals x plus y plus z, right? And now while generating code, since fields are bound statically, the compiler can actually generate offsets for which field you plan to access statically during code generation itself. So a compiler might generate code like the following. Let us say int m1, and we had said that those x and y's are actually this dot x and this dot y, isn't it? So let me pass a pointer to this explicitly here so that I can write it. Okay, what is the type of this here? What class does this belong to inside m1? A, right? This is a pointer of type A. So let me create a explicit pointer and let W this for winter school this, because this is a keyword, so let me just use another name here. So let's say I have a special parameter. The this pointer is usually implemented as the 0th parameter of your method. So you have explicit parameters like z, and there is an implicit parameter this, which I have made explicit by writing it over here. And then let's say I have an integer variable z. So let's say the compiler first converted the prototype of m1 to something like this, right? And now when it writes code like this, it would say int t1 is equal to, instead of x, let me make it explicit. Which x I am talking about here? W this dot x, right? So let me say w this dot x plus which y am I referring to over there? W this dot y. And which z am I referring to over there? Just the z, the parameter z. So it need not be qualified with anything. And then of course I could say return t1. This also means an interesting thing for the call sites of the method m1. Yeah, so we had, let's say, allocated an A type object somewhere. Ax is equal to, I hope you can see this, ax is equal to new a. We had said x dot m1 is the way you would call the method m1, right? So now since and m1 required an integer, so let's say I was passing 5 to it. Okay. So now if I have changed m1 to look like this, what should I change? The compiler should, how should the compiler change the call site to m1? So let's say, no, I need to pass x separately, right, as the first argument. So I would say, let's say m1 x comma 5. Does it match the expected signature of m1 now? There is an A-type object passed first, a reference to an A-type object passed first, and then an integer variable which matches with this, right? So let's say this is the code where I have just made things explicit by passing the this pointer explicitly, and now since fields are bound statically, the compiler can actually generate code instead of doing this dot operation, the indirection, the dereference at runtime. The compiler can bind this field statically because the compiler fixes the size of an A-type object and a B-type object. Let me just draw the A-type object again for our quick reference. We had address of the V table of A and then a field X and then a field Y, 0, 4, 8, and this is a class A object, 12 bytes, right? So now the compiler fixes the structure and hence compiler can avoid these dereferences to happen at runtime. It can actually optimize this code while it generates this code. So instead of, let's say, the compiler, instead of saying w this dot x, can change it like this, m w this int z, and here int t1 equals 2. Now if x is pointing to an object that looks like that, the A-type object over there, can you help me avoid this dereference and replace it with an index into that object? Right? That object is just an array, right? Let's say it's just an array. At index 0 I have stored something, at index 4 it's an array where each element is of 4 bytes. Let's say each index is, instead of 0, 1, 2, let's say I can access that array directly at 0, 4 and 8, right? It's a low level structure. So instead of w this dot x, what could I have written now? W this 4, very good. W this 4 plus, instead of w this dot y, what could I write now? W this 8, and this guy z can remain as it is and return t2. What does this mean? The compiler, because fields are bound statically, is also able to generate the offset at which a field is stored with respect to this pointer over here, right? And hence at runtime you don't need to do any special magic. At runtime this object w this will be allocated in the memory at some location, right? It will be, let's say, really allocated at some address 1000. So compiler, or rather the linker would just, or sorry, the loader would just make sure that this is 1000 plus 4, this is 1000 plus 8, and it will just store the address over here. You would directly access the field from an address instead of performing dereference at runtime, and hence fields are fast to access, right? The cost for fields comes when they are, let's say you w this dot 4 is actually another object pointer. Then you access that object again in the memory somewhere. Then you access its field somewhere else in the memory again, and so on. So the cost of field access essentially comes from indirections made to follow different pointers. But the address of each field inside an object is determined by the compiler itself. Alright? All of you with me? Now let's look at some code where we have to call a method. Let's see here. Inside m1 I have a call here, int t2 is equal to m2. So assuming we know the class B structure, we know class A structure, and so on, let us say I try to write the code for the method m1 of class B. So int m1 int, or before int let's pass an explicit pointer again. This is a B type pointer, let's call it w this still, we can give it any name local to a method. And then let's say int p, right? Now the first line of this method is int t2 equals m2. So int t2 equals is okay, this is just a local variable. You know that these local variables are also replaced by the compiler, right? It need not write like this int t1. Instead of t1, it would write some offset with respect to the stack pointer. So local variables are anyway on the stack. You know the offset to each variable on the stack, and they are with respect to the stack pointer. So the compiler, while generating code, will not refer to this as t1, it will refer to it as some offset on the stack frame of the method m1. Okay, so stack addresses are anyway very fast to access because you know the offset already. And similarly for fields, you know the offset here because the fields are bound statically in Java. Okay, now let's come to the method again. So when you say int t2 equals m2, a call to m2. Now how do I call the method m2? Where is the pointer to the method m2 stored? Yeah, it's stored in the v table of class B. Well, this points here and then it's stored over here. M2 is stored over here at index 4 of the v table. How do I get the address of the v table? Here. Yeah, w this of 0 will give me the address of the v table. And now from here, since I want to call method m2, which offset should I index to? 4. Yeah, this of 0 of 4. And then maybe a call is just like this. Wait, what should I pass to the method m2 now? Do I need to pass something? Method m2 also would have been changed in a way that it takes, let's look at method m2 here. It does not take any argument by default, but I would have changed it to take the this pointer by default. I mean by explicitly. So how do I pass the this pointer to m2? I'll just say w this. I'll pass it explicitly, right? So the compiler, while translating code, would change it like this. And then as you can see, there is a vtable lookup involved over here, which makes it expensive. Okay, there are two levels of indirection over here if you see. So method calls are more expensive, and if the method is overridden, what would happen? So if let's say I have a B type this pointer, if you remember, if let's say this was an A type object, A type reference, it can point to an A type object as well as a B type object, right? It can point to either a parent reference can point to a parent object or any of its descendants objects. That's what we had seen yesterday. So now if this is an A type object and if I were to call method m1 from it, it's at index 0, and automatically if that was a B type object, since I have overridden the method m1 over here, there also index 0 will automatically call the overridden method. So this trick helps as well because you can directly assume that at the index that you would determine for a method, you can directly get that method. Makes sense? Okay. So having seen how would you store each object conceptually, now let's look at a tool that allows us to look at the structure of these objects for any Java class. Okay, so there is this tool called as JOL, Java Object Layout Tool, which you can download. There is a jar file, you can download it from internet, from Oracle's website. And so here it's this JOL CLI latest.jar. Okay, and let's say we have some code here, jol test.java, or wait, we had said that there is a class that already exists in Java, right? The parent of anybody who does not have an explicitly declared parent. What is that class? java.lang.object, right? What should be the structure of java.lang.object? Well, there is no field in that class. Okay, so if you want to see what's the structure of that class, if there is no field, you may still have some memory at the top to store metadata about the class, but no space about its fields, right? So let's see the structure of java.lang.object. Okay, so its usage is like this. You just give the full path of the object over here and write the word internals and refer to this jar, and it actually gives you a lot of information. It says I have a 64-bit VM here, and the sizes are like this. References are 4 bytes, boolean is 1 byte, byte is 1 byte, character is 2 bytes, short is 2 bytes, int is 4 bytes, float is 4 bytes, long is 8 bytes, and double is 8 bytes. This is the size of each kind of variable on my machine for this Java virtual machines installation. And it also tells about array element sizes, array base offsets. Since we are not working with arrays for the time being, you can ignore this. And then it says what would be the size of, or what would be even the structure of an object of Java Lang object class. Okay, it says at index 0 of 8 bytes you have something called as object header, and there is a mark bit over here. At index 8 for 4 bytes you have an object header with some class field over here, and then at index 4 you have some object alignment gap. Total size of an object of Java Lang object is 16 bytes. We'll understand what is this padding and so on in a moment, but I hope you know the you know the syntax of this output right now. Let's look at it for some classes whose structure we can conceptually understand. So let's say I have a class here. Well, static classes in Java can be declared just inside other classes like this. Don't worry about them. Even if you take it out and write this int class outside somewhere, it's okay. This is just for my convenience that I have declared it inside another class. But I have 4 classes here: int class, int boolean class, long class, and long int class with appropriately named fields. So int class has an integer field. That's it, right? Int boolean has an integer field and a boolean field. And so now let's try to understand the structure of these objects, and you would see it matches with our understanding. So now let's compile this jol test.java. If you do an ls now, you see lots of things. There is a jol test.class, and we had said there is a .class file generated for each class inside my Java file, right? So we had int class, long class, and so on, and if they are nested classes, then the JVM prepends it with the name of the host class in some sense, okay, the enclosing class. So it just says jol test dollar, inside it you have int class dot class, jol test dollar long class dot class. This is just a convention, a Java convention, okay. So you have a class file for each of the classes inside it. Now let's try to see the structure and understand it. Yeah, so now here I have, let's say, not java.lang.object. Class path says try to find the class in the current directory. -cp dot says, oh, Java Lang object is by default there in the Java installation. Since I am looking for the structure of a class in the current directory, I have to add it with the cp command over here, cp argument over here, and then I can write the name of the class whose structure I want to see. Let's say, so, and you have to put a backslash here before the dollar, int class, like this. Okay, so this will tell me the structure of int class over here, and let's see. It says, so this part, as you can see, it's repeating again, right? And then the interesting thing comes here. It says at index 12, it has an integer of 4 bytes, and it gives the name of the integer field as well, int class.v. There was a field int class.v, as you can see over here. There was a field v inside int class, and it says it's stored at index 12. So instead of, the only difference that you see over there is, instead of these 4 bytes for the v table, how many bytes you have stored at the in the top of each object, top part of each object? 12 bytes, 8 plus 4. Okay, there is something called as mark, something called as class outside the scope of this winter school, but let's just you can understand it like this. The object, you need for each object the address of the v table, the address of some more information about the class, some metadata that's used for garbage collection and locking in future and so on, and all of it is spread across 2 pointers, the class pointer and the mark pointer. The mark pointer is 8 bytes, the class pointer is 4 bytes. The class pointer actually contains the pointer to the v table, and the mark pointer contains information about other metadata information, as I mentioned just now, for locking and for garbage collection and so on. So there are 12 bytes on my machine. The size of the metadata or the header of the object, which is separate from the fields, is 12 bytes. That 12 bytes also, those 12 bytes also include the memory for the v table's address. Okay, and then you have the field over here, which is of 4 bytes since it's an integer. So the size of the object is 12 plus 4, 16 here. We'll see what is this space losses very soon, but here there is no space loss, it's just 16 bytes. All of you with me till now? Now, what would you expect the size of? Let's try to look at which one did we have? Int boolean, let's say. What would you expect the size of an object of the int boolean class to be, ideally? 12 bytes for the header are fixed, then 4 bytes for integer, and boolean, it says here, right, boolean requires 1 byte over here. So ideally what should be the size of an object of this class? Yes, 17 bytes, right? But let's see, it says it's 24 bytes. Okay, and now it tells us why. So you have at 12, index 12, you have an integer field v1 which is of 4 bytes. At index 16 you store a boolean here, and then from 17 there is an object alignment gap of 7 bytes. Does anyone know what is this alignment gap and why would it be needed? I think this battery is gone. No, yeah, it's showing red, so I think it will go. Have a 64-bit boolean here, which means if I have a byte addressable, thanks. If I have a byte addressable memory, I can't really start at arbitrary boundaries. I can start only at multiples of 8 in order to generate addresses, right? So if I have an object stored from 0, the next object can either start at address 8 or 16 or 24. There is no way to access in between. So it's an architectural convention here, because of which we need to leave some space here to align objects to the addressable offsets in memory, and hence there is an alignment gap of 7 bytes, and that's what it calls a loss. There is a 7 byte external loss. We'll see what is an internal loss soon here. External loss means that 7 bytes is needed to make sure the next external object starts at a multiple of 8. Okay, so now let's look at the other one. What's the third one? We have long class. What's the size of a long field? 8. So if you see here, there is now an internal alignment gap introduced. So 12 bytes are reserved for the header, and then from 12 to 14 it says I can't store a long at 12. Since a long is of 8 bytes, I can only start a long from offset 0 or offset 8 or offset 16 or offset 24, a multiple of 8. Since a long is of 8 bytes, I cannot start it at 12, which since it's not a multiple of 8. Similar reason, so how do I access inside an object? If it's an 8 byte object, it can only be accessed at multiples of 8, and hence you have an internal padding done here, which is a space loss of 4 bytes within the object. Okay, it's in some sense just a wasted space, right? But we can't do anything about it. But the JVM tries to be smarter, as we would see in the next example. Very good question. If you were in a course, I would give you participation credit, as I call it. The question is, we said references are 4 bytes, but it clearly says at the top, oh, it's a 64 bits addressable space. So I should be required to have how many bytes to address? I should have required 8 bytes to address objects in my memory, whereas I am keeping only 4 bytes to access objects in the memory. And the key is here compressed references. This is a very interesting feature. Let me explain to you. And now we can use black here, so don't, no problem with rubbing it. So since anyway you cannot access objects from arbitrary boundaries, you can only access objects at addresses that are multiples of 8. If I have a 64-bit address like this, let's say there is a 64-bit address here, which is needed. I need 64 bits to actually address objects in my memory, I should have stored 8 bytes. What would the last 3 bits always be? Since I cannot access objects at boundaries which are not multiples of 8, what would the 3 bits for each address be? 0. These will always be 0. Now can you guess why? Can you extend my answer and tell me why a 4-byte reference is enough to address a 64-bit addressable memory? What might the compiler be doing, or what might the JVM be doing over here? It always knows that the last 3 things are 0. So I don't need to store them. To any address, I can just append those 3 zeros to generate the actual address. I don't need to store them, which means I can get rid of 1 byte, addresses of 8, I can get rid of 1 byte and I can just address it with 4 bytes. So a 32-bit address space is enough to address a memory that requires 64 bits to address all its bytes, but the last 3 ones need not be accessed directly, so you can just append those zeros. Learn about compressed loops. It will show you even the formula, how does it append, how does it XOR, and how does it generate the real address, and so on. It's interesting that all those zeros can be just appended while generating the address. You don't need to really create addresses which require 64 bits in them. You can just work with 32-bit addresses over here. It's called compressed OOPs. Yeah. Ordinary object pointers. OOPs means ordinary object pointers. Okay. And it compresses those pointers because it knows that it can infer the last few bits to be zeros. It doesn't require to store them, and hence you don't need 8 bytes to here to access a 64-bit addressable memory. Okay, let's come back here to what is more relevant for now. But I hope you see that's a very good observation. Okay. All right, so now let's look at the next one. Here we said we are wasting 4 bytes here because we cannot store a long starting from 16. Now let's see, we have an interesting example here. We have a long here for which we observed a wastage of 4 bytes, but then we have a long int class here. Look at its structure. It has a long field as well as an int field. How much space does an int field require? 4. So now see what does the JVM do. Long int class. The previous one also required 24 bytes and this one also requires 24 bytes. What did the VM do? Can you read this and tell me what happened? Why do you still need 24 bytes even when you had one extra field? It utilized that gap by storing the integer. It swapped the order of the fields. Instead of storing the long field first and then the integer field, it saw that, oh, I anyway was leaving 4 bytes of alignment gap in between, let me just put it there. Because if I did not put it there, I would put it at address 24, which means I would actually waste 4 more external bytes over here. So 4 plus 4, 8 bytes would be wasted, and that's not needed because I can just swap the order and fit it in the alignment gap, okay, in the internal padding gap, right? So that's what it did. If you see here 12 to 16 was just a gap, whereas it has fit in that long, the int field of 4 bytes at that space. Okay. So this is something the JVM does. So these are interesting things to know, because when we teach something in the class and if we have some way of visualizing what really happens in the particular runtime or in the particular compiler generated code, we can actually figure out how or what are the differences in explaining something conceptually and what all things a real compiler or a real runtime in this case might be doing internally, to what all tricks it might be implying, for example, right? So it does a trick to fit in it in the alignment gap and swap the order of the fields. It need not have to generate all the fields in the order in which you have declared at the top, right? This makes debugging a bit difficult, to be honest, because if you are debugging your program and you expect based on the layout of the fields that you have created, you expect some field to be present at a given offset. but then the compiler might have reversed the order or changed the order for doing some optimizations like this, fitting in things in here, right? So you have to be careful about compiler optimizations changing your expectations when you debug your programs. Any questions here? So for an integer field, you can access it at any address which is a multiple of 4, right? No. See, what is the size of an integer? 4 bytes. So you can address it, you can store an integer at any address which is a multiple of 4 inside an object, right? If you had an 8-byte field here which is long, you can access it only at multiples of 8 with respect to the offset within an object. Why are we aligning objects at 8 bytes instead of 4? Because in reality, for 64 bits, you need 8-byte addresses. So the next object can only start at a multiple of 8 over here, even though we are requiring only 4 bytes to store its address. That's an optimization again. Right? That's the compressed oops trick as we discussed. But in reality, what's the size of a reference? What's the size of the memory required to access addresses of objects in my RAM? 8 bytes. Each address is 8 bytes totally. I am not just storing them. Yes. Yes. Right? You can count it and it will come in. Okay. Let's look at one more. I have one more with inheritance, then we'll move on. So I have another class here where we have a class A, then class B extends A and class C extends A, which means how many fields would be there in a class B object? 2. How many will be there in a class C object? 2. So let's just have a look at that example as well, just to be sure that, oh, the parent fields are also there inside the child object as we have seen just now. So let me compile this and then we'll just use JOL to visualize its structure. Inheritance field test1 $A, I think. Yeah. So A has 12 bytes of header and an integer field as expected, total 16 bytes. Now look at the structure of a B class. A B class has 2 fields here, an integer field A of the parent and integer field B of the child, and then an alignment gap for the object. So total it is 24 bytes. If you look at the structure of the C class, it's also very similar, an integer A field, then integer C field of the child, and then an object alignment gap, total 24 bytes. So this is as expected, but there is one interesting thing over here. If you look at the next example where I have a long field in my parent and 2 more integer fields in the child. Now you know that in the child you would need all these fields, you would need this long, for simplicity let me just remove it once maybe. I have V1 in class A and V2 in class B, okay. Now let's just compile this inheritance fields test2.java file and to $A. Yeah, so it has a long field as expected after the alignment gap because long needs to start at a multiple of 8. And if I have B here there is something interesting. It has swapped the order between the parent and the child fields again to make sure that you are utilizing these 4 bytes internally. Okay. So one thing to note is that if you are using something which is less than Java 15, I mean a version of Java which is until Java 14, Java 8, 9, 10, 11, 12, 13, 14, any of them, you would not see this happen. You would see that first it lays out the parent fields, then it lays out the child fields, which means there will be a 4 bytes gap over here. And then since the integer field is 4 bytes, there will be an external gap for 4 more bytes. So the size of this class B object for a Java version prior to 15 would be 32 bytes. Okay. whereas they realized that, oh, if we change our field layout algorithm and if we allow child fields to be laid out before parent fields, we could probably take advantage of the internal gap that has been created, which means we can reduce the size of an object. If I am creating 1 million objects of this class B, let's say this class B is a very popular object, there is database stored of all the people in a city, there are 1 million people in that city, and for each of those we create this class B object and store it in a database. We would require 8 bytes of extra memory for each of them. So 1 million times 8 million bytes of memory, which will be how much? Can you tell me in terms of gigabytes, terabytes? 8 million bytes, how many gigabytes it is? Keep removing 3 zeros. I'll just trust whatever you tell as the first answer. Huh? 1000 GB? Okay. Maybe. 7.6 megabyte. Oh, not 1000 GB. Okay. I don't know. So something. So assume that that much amount of memory will not be needed anymore if you are using something beyond Java 15 or some later version of Java, right? So it will be some significant amount of memory, as you can see over here. So there was this trick that came in Java 15, and let's just complete it by adding the field that we had removed over here. We had an int v1 just to demonstrate that fields of the child class do not really override the fields of the parent class. You would be able to see in a class B object here, there is this integer b dot v1 stored first, and then long a dot v1, and then you again have integer b dot v2. So it's just trying to minimize the space required for storing an object by utilizing the internal alignment gaps, internal padding gaps, as we had seen over here, right? And the total size of the object is still 32 bytes. Even if there was one more integer field, I could have put in over here, or if there were 4 more boolean fields, I could have put all of them over here, and my object size will still be 32 bytes. Does that make sense? So this is a trick that Java 15 implemented in the VM. Okay, any questions? I don't think I have Java 8 here, but yeah, if it's there, since it's there on your the Docker images that have been shared with you, it has Java 8. Maybe you can try one of these examples in your Docker VM and try to run JOL if it's there. You would see that it actually does not swap the order of parent and child fields. The first lays out parent fields maybe with some gap, and then the child fields maybe with some gap, and then the object size would be more. Okay. So this is what I wanted to cover about object structures, and now as we have seen, there is a cost associated with storing the size of storing an object and then accessing the object's pointers. There are various things here. If I did not create something as an object, instead I created that thing as local variables on the stack frame, how much memory would I save? 12 bytes. We have seen in reality those 12 bytes of header is coming in just because of an object. So if I were to create an object which has just one integer field, 4 bytes, that's the amount. So if, let's say, when you write programs in O languages, we keep writing like this, right? We'll say, oh, class A with one integer field x, or let's say I have a class point. You are creating a 2D point in your program and you have two fields here, int x and int y, right? I really need just 8 bytes to create this abstraction of a point, but how many bytes am I actually asking for? So I am actually asking for 12 bytes instead of this, right? So now the question is, there are lots of costs associated with object-oriented programming, right? One is the size of the object itself, 12 bytes of header that come extra along with each object. Second, if let's say I were to let's say I have a program like this. How do you compute the distance between 2 points in a 2D plane? Let's say I have a method foo over here and I create 2 point objects, point P1 equal to new point 2 comma 3, point P2 is equal to new point, let's say 3 comma 4, and I have some method here, some method that's called some distance method, let's say r is equal to, so how do I calculate the distance between 2 points? Euclidean distance, yeah. Correct, x2 minus x1 whole square plus y2 minus y1 whole square if I am computing the distance between the second point and the first point, and then take a square root. So let's say that logic is implemented in this distance function, okay, and I am passing p1 and p2 to it, right. Now in the distance function I'll get two parameters, point p1 and point P1 and point P2, and I would, in order to get x2, what would I do? I'll say p2 dot x square somehow, so there will be a call to a square function here, minus p1 dot x square plus p2 dot y square, and then there is a square root here, and then I return it, and so on. See, I'm mixing mathematical notation with Java here, but that's okay. So this is how I would write, this is how I would access the fields of these objects. And now let us say my task is I am writing some image processing application for which I have to compute the distances between millions of points in some image. Based on that, I want to transform the image. If you use Lightroom, you might want to, let's say, put a mask there and so on. So all these computations that go on images, for example, keep computing distances across thousands of points throughout the image, for example. For each of them, you are allocating so many points first of all. You are creating 12 bytes of extra memory for each of them, and then you are incurring a method call. A method call, if it was something dot distance, then again you would go to the v table, you are incurring indirections. Maybe this method is being called in a loop for a pair of all the points in your images, so millions of times, let's say, and then in the method itself you are accessing the x and the y coordinates again and again, which means here you would have an indirection, here you would have an indirection, some offset, you will go to that location, and then for y and so on, and then you will do the square root. So much of this computation overhead is just coming from the fact that we had point allocated as an object of a class. What if I did not do that? How could I have written this code instead? Instead of creating these 2 points separately, I could just have used 4 integer variables here. Struct will have similar costs as point to a large extent. So let's say I just created 4 integers, x1 is 2, x2 is 3, or y1 is 3, x2 is 3, and y2 is 4. I just created 2 integers. Instead of incurring a method call here, let's say I just decided to compute the square root by directly using those variables. So I would have avoided this extra storage space for the objects. I would have avoided the time for this method call. I would have avoided the indirection incurred while accessing the fields, and so on, right? So then we should just get rid of all structures, classes, objects, method calls, field indirections. We should just get rid of all of them. Why to even learn about all of these topics, right? What do you lose if you have to write with a programming language that doesn't support all of this? Yeah, the abstractions. Well, the programmer can no longer talk in terms of points. Let's say you wanted to create 1 million points here. You will have to create 1 million variables. 2 times 1 million, forget 1 million, that sounds too high. Let's say 100. I have to create 100 points. I'll have to create 200 variables. I'll have to make sure that when I do x2, when I do p2 dot x here, I should make sure I have done, let's say I'm talking about the 517th point. I should make sure I do 517 minus x516, let us say. And when I do this for the y coordinate as well, it should be x517 minus x516. If I just change that number by mistake, I would end up calculating something else and the program will go wrong, right? So the loss of abstraction is important for the ease of programming, and it's huge. If you did not have this abstraction here, just imagine making sure that 516 is used when 516 is needed, x 516 is used along with y 516. So many errors you might end up doing while writing such programs, isn't it? And these abstractions allow us to write several kinds of programs which are so easy to write without bothering about associating the x and y field of this object separately from this one and so on. We don't need to worry about all of it. So object oriented programming in this case gives us huge benefits in terms of being able to write programs that you can understand, that you can make sense of, that you can avoid errors on, but it comes with so many costs. It's the compiler's job, or many compilers try to get rid of all these costs. So it's the idea is, let the programmer write good beautiful programs without worrying about low level efficiency, and write a better compiler, train people more on in ACM Winter School, make better compiler designers out of them, so that they can take care of all the overhead under the hood without making the programmer having to worry about writing ugly programs which are good but very low level or error prone, for example, and so on. And that's the job of today's programmers, today's compiler designers, right? Because languages are getting more and more high level. Programmers don't come from CS background, so who should get better? People who understand such low level concepts should get better, so that you can fill the role of software, or you can create software like compilers which fill the role of bringing in efficiency to such high level programs. Okay, so we would see several optimizations in the next session after the break, where we would try to, or at least we'll get an idea of few optimizations performed by modern real world compilers that try to reduce at least some of this cost. Can I get rid of the header? Can I get rid of object allocation overheads? Can I get rid of deallocation overheads? See, we didn't even talk about deallocation till now. If this was C++ and I allocate 1 million objects like this without freeing them up, I might not be able to run the program on even a RAM laptop with, let's say, 64 GBs of RAM. Why? Because I'm never deallocating memory. I'm allocating several hundreds of gigabytes of objects. Right? Again, if you were writing in a language where you can deallocate memory like C or C++, you have to think where to deallocate memory, where to write a free instruction, where to write a delete instruction. And again, it's a natural progression where you would say, oh, let me not burden the programmer about where to deallocate memory. Let me do deallocation under the hood as by writing a garbage collector. Right? So that's another example. Can we take care of allocation overheads? Can we take care of deallocation timing? Can we take care of method calls, or can we reduce the cost of method calls? Can we reduce the cost of field access and so on? And there are several optimizations that are performed by modern compilers to do all this, at least to some extent. Okay, and a lot of research goes behind improving what they can do. Like we saw in 2015, oh, a small tweak can reduce a lot of memory requirement at runtime, right? So these, as we progress in the next few sessions, you may also be able to see some places where you can improve. Okay, any questions? I hope I have excited you enough for these kinds of optimizations. We'll talk about them after the break.